Good morning, everyone. This is Saujanya working as Assistant Professor in CSE Department at GRIT. In this lecture, we are going to learn about the next topic in the virtualization, that is virtualization of CPU, memory, and I/O devices. Latest processors employ a special running mode and instructions to support virtualization known as hardware-assisted virtualization. This point we already learned in the last lecture. The virtual machine monitor and guest OS runs in different modes, and all sensitive instructions of the guest OS and its applications are trapped in the virtual machine monitor. To save processor states, mode switching is completed by hardware. For the x86 architecture, Intel and AMD have proprietary technology for hardware-assisted virtualization. How this hardware supports for the virtualization. Modern operating system and processors permit multiple processes to run simultaneously. If all instructions from the different processor try to access the hardware directly, that may lead to crash. To ensure uncontrolled access of the critical hardware process have two modes. One is user mode, second one is the supervisor mode. Instructions running in the supervisor mode are called the privileged instruction. Other instructions are called unprivileged instructions. Popular hardware virtualization products are Virtual VMware, Zen, and KVM, etc. In the hardware support virtualization in the Intel x86 processor, now we will see how it will work. Since software-based virtualization techniques are complicated and incur performance overhead, Intel provides a hardware-assist technique to make virtualization easy and improve performance. Here is the diagram which will show the Intel virtualization technique for processor, memory, and I/O devices. See here how it will be work. Here the processor, this is the hardware part, and the top of that one we are having the different virtual machines. So here we are having that virtual boxes like VTI, X, EPT table, and DMA and interrupt remap, shareable. How this network and storage will be shared between that virtual machines to the host machine, and here VTT, and let us see what was this one VTX and everything in the next. For processor virtualization, Intel offers the VTX or VTI technique. VTX adds a privileged mode, VMX, root mode, and some instruction to the process. This enhancement traps all sensitive instructions in the virtual machine automatically. For memory virtualization, Intel offers the EPT, which translates the virtual address to the machine physical address to improve the performance. For I/O virtualization, Intel implements VTD and VTC to support this. Then CPU virtualization. A virtual machine is an image of existing computer system. Unprivileged instructions of virtual machine run directly on the host machine for higher efficiency. The critical instructions are divided into three categories in the CPU virtualization. Those are privileged, control sensitive instructions, behavior sensitive instruction. What is meant by this each instructions we need to learn now. Privileged instructions executes in a privileged mode and will be trapped if executed mode outside this mode. Control sensitive instructions attempt to change the configuration of resources used. Behavior sensitive instructions have different behavior depending on the configuration of resources. A CPU architecture is virtualizable if it supports the virtual machine privileged and unprivileged instructions in the CPU's user mode while the virtual machine runs in the supervisor mode. When the privileged instructions, including control and behavior sensitive instructions of a virtual machine, are executed, they are trapped in the virtual machine monitor, and the VMM acts as a unified mediator for hardware access from the different virtual machines. Next, we will see about what is the hardware assisted CPU virtualization. Intel and AMD and an additional mode called the privileged mode level. This is available at the ring 1 in the x86 processor. Therefore, operating system can still run at ring 0 and the hypervisor can run at the ring 1. All the privileged and sensitive instructions are trapped in the hypervisor automatically. This technique removes the difficulty of implementing binary translation of full virtualization. It also lets the operating system run in the virtual machines without modifications. Next is the memory virtualization. The x86 CPUs operate on one-stage mapping from virtual memory to the machine memory. However, in a virtual execution environment, virtual machine virtualization involves sharing the physical system memory in RAM and dynamically allocating it to the physical memory of the virtual machines. That means a two-stage mapping process, virtual memory to physical memory and physical memory to the machine memory, should be maintained by the guest and as well as in the virtual machine monitor. Here we will check about the two-level memory mapping procedure. This is just like that in operating system only. The guest OS control the mapping of virtual address to the physical memory address of the virtual machine. Since the guest OS cannot directly access the actual machine memory, the virtual machine is responsible for mapping the guest physical memory to the actual machine memory. Here virtual machine 1 is there, virtual machine 2 is there. So here two level mapping, memory mapping is there here. How the memory here, if we are having the memory concept, that complete memory is divided into number of blocks. So first of all, before going directly that memory into the virtual machine directly for each processor, but here the virtual machine first level will be there, then second level of virtual memory will be given to the virtual machine 1 and virtual machine 2 and virtual machine 3 and so on. So that's the reason we are having it we are calling as a two level memory mapping procedure. Here first is the machine memory is available here, that is the first level. Second level is the physical memory is available here, physical address, then virtual memory available here. Next, shadow page table. Each page table of the guest OS has separate page table in the virtual machine corresponding to it, known as shadow page table. The MMU handles the virtual to physical translation as defined by the OS. Then the physical memory address are translated to machine address by using another set of page tables defined by the hypervisor. Since operating system maintain a set of page tables for every process, the shadow page table will get flooded. Consequently, the performance, overhead and cost of the memory will be very high. Virtual machines uses shadow page table to perform the virtual memory to the machine memory. Here, process use translation look-aside buffer hardware to map the virtual memory directly to the machine memory to avoid the two levels of translations on every access. When the guest OS changes the virtual memory to a physical memory mapping, the virtual memory monitor updates the shadow table to enable the direct lookup. I think you can understand what is the virtualization CPU, IO and memory, right? Thank you all.